I've got another question here by KG Moila, and then he has given us a structure that he wants us to help him answer. So here it says, a generator is shown below. Already, I love doing this. When we talk about a generator, we know we talk about mechanical energy, because chances are they're going to ask you mechanical energy, and we convert that into electrical energy. Electrical energy. Now assume that the coil is in a vertical projection. Dun, 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 dun. What does this tell us? I want us to go back to my beautiful drawings here. This is then where we must take into play. Remember? Because as it is turning, it's either perpendicular. If the magnetic field is moving in this way, it's either the magnetic flux is at a minimum or the magnetic flux is at a maximum, depending on the position that it is. So let's see, what else are they telling us here? Is in a vertical position. I've got my magnet here, which is my north. I've got my south. Then I already know my magnetic field moves from the north to the south. So now they're asking us a question here. Is this generator above an AC or a DC, and give a reason for your answer? And we have 2 marks. What are the examiners looking for? They want you to say whether it's DC or an AC, and then to say why. Now, going back to Mpendulo's question, where we had looked at the differences and the principles between AC and DC, now we have to go back there. One of the biggest things, okay, we know they both use Faraday's law, they convert mechanical energy into electrical energy, but the biggest difference between the two was the different components or parts that whether make it AC or DC. So let's answer this question. So this is 9.1.1. So 9.1.1, is this AC or is this DC? So my answer, it is a DC. And how do I know that? Because look here, it has got a split ring. This is a split ring. This is a split ring. And remember what we said? Some people call it a commutator. Mutator. Because if it was an AC, I just want to take you back a little bit. We were going to have 2 rings like this. We were going to have something going there, something going there, and then we were going to have our carbon brushes on the side. This then would have been for an AC to show that the current is alternating. But in this case, there is a split ring, or a commutator, right? So in my answer, I've given my reason. It is a DC generator. And they're going to ask you, why is it a DC generator? So you can say, because it has split rings, because split rings are present, because I'm just going to say, because it has split rings. It has a split ring. Has a split ring, or you can also say a commutator. Mutator. Right, so that's what the examiners are looking for. Let's look at another question. So in 9.1.2, it says we must sketch exactly what I was talking about. We must sketch an induced EMF. Now they're already telling us an induced EMF versus time graph, right? For one complete rotation of the coil. Right? The coil starts turning from the vertical position, and this is going for 2 marks. So let's see how we're going to do this one. It must start rotating from a vertical position. So this is 9.1.2. So this is only for 1 rotation. Let me just take you back. So now remember, we have A, it'll change, it'll change, it'll change, it'll change. It has a 360 revolution, going back to Mpendulo's question where we had to draw the graphs. So in our case now, we are going to have to draw 1 full rotation. Now, guys, remember, let me actually do it with you. When you are drawing a graph, you must write a heading. I'm just going to write heading there, because you actually do get marks for having a heading. And then you must also indicate what is on your vertical axis. In this case, we have an induced. We have an induced EMF. And if you feel like you're forgetting, if it's always in comparison to time, time will always be in the horizontal side, which is in seconds. Now let's draw 1. Now, in this case, they didn't give us any values. They didn't tell us whether Vmax is 340 or 220 and so forth. So we can just draw the graph because it's for 2 marks. However, if they had given us maybe values, it would probably be for 4 marks, because you needed to show the examiner that the amplitude of this way of the graph would have reached the Vmax or so forth. So make sure that if you are given values, you plot in your values, and if you're not, then it's just they just want to see if you're able to see the structure. So in this case, remember, we're going to have a little bump, and then we're going to have a bump. This is a DC. If it was an AC generator, we were going to have a sine graph because the current, I always like to say it slips because it has a slip ring, right? And then it forms a little S, right? Remember, when things fall, you kind of like, whoops, have a little whoopsie, and that is a slip ring. So that is then how we were going to draw this graph. 2 bumps for a DC generator. Now let's move on. That was for 2 marks. Ooh, then we have some calculations. So we have an AC generator, AC in alternating. Now we already know it has slip rings in operation at a maximum. So remember, when they talk about maximum, they're talking about Vmax of 340 volts. It is connected across a toaster and a kettle as shown in the diagram below. Okay, this is my generator. I've got a toaster and I've got a kettle. Now, this is 800 W. This is 2000 W. Now, going back to grade 11, we know our SI units and we know that a capital W means power. So this means 800 watts and this means 2000 watts. Now, going back to electricity, I can see that the current will come. It'll split and then it'll split. So this is a parallel circuit, or it's connected in a parallel dimension, right? So this generator must produce power here and it must produce power here. It requires 800 watts, 2000 watts. Now it says that the toaster is rated at 800 watts while the kettle is rated at 2000 watts. Both are working under optimal conditions. And then the question further says we must calculate the RMS current passing through the toaster. Ooh, so we are looking for current. Now looking at your exam, your formula sheet. Now you must remember that current is represented by a capital I. We have a capital I for current and this is RMS. Now I'm just going to use my formula sheet and this is for 3 marks. So let's see how we can answer this one. Let's work on this one. So this is then, we have this is 9.2.1. So we must calculate the RMS current passing through. Okay, so the one way we are given power. So I can say power average is equal to VRMS, right? This is from your formula sheet, and IRMS. But then I don't have VRMS, I have Vmax, and I know, I just want to branch this off. If I have, let me use a different color. If I have VRMS, I know I can say Vmax over the square root of 2. So I'm going to have power. And I always say, guys, write everything down so that your examiner can see where you're going. So I'm going to say VRMS all over my square root of 2. And I've got IRMS on the side. Now, I'm given the power. Remember, they're looking for the power of the toaster. They're looking for the power of the toaster. And I'm given the power as 800. So that's the power that I'm going to be using. The power is 800. So my power is 800. So I'm putting my power. And guys, one mistake some of you guys make is that if you are looking for an unknown like current on this case, you so much just move the current to the power and you move the power on the other side. You don't do that. You have to put in all your values and then according to mathematics, you must make something the subject of the formula using mathematical rules and then you are able to solve it. But I'm going to show you. So here we have 800 and then my VRMS, I'm going to have 340 over the square root of 2. And then I'm looking for IRMS. I just want to think this one. This is Vmax according to my formula sheet. This is Vmax, and my Vmax was given to me. Let's just double check that quickly. My Vmax was given to me as 340. Yes, my Vmax was given to me as 340. So now let's plug in and see what we are going to find. So now I need to make something the subject of the formula. IRMS current that is required for the toaster. So now I've got a calculator in front of me. I'm going to do this part first because I always think it's always better to have small numbers. I'm going to have that under the square root of 2. So it is 240 points. So I'm just going to leave it to 2 to 3 decimal places, or you can write down the whole number. Just to be more accurate, I'll leave it to 3 decimal places. So I still have my 800 on the side. I'm going to have 240, that was 416, yes, and IRMS. I'm looking for IRMS, so I have to divide both sides with what is irritating my IRMS. So I'm going to have 240, 416 on this side, and again on this side. 416. Remember, don't round off to the end, otherwise you're going to get a very vague number. So now let's see. So I'm just going to say 800 divided by the answer we just got. Wow, so that gives me 3.33. So this 7 is going to change this 2 to a 3, taking it back to grade 9 when we did rounding off, right? So the 7 will round off the 2 to a 3, and then we get 3, we're going to get 3.33, and that is A. Remember, when we measure current, we use an ammeter, but it's measured in amperes. So another way we can do it, looking at our formula sheet, we can do it the long way around. I can first find my VRMS. So if you wanted to go that route, so if you can say VRMS first, and that is Vmax, because we do have Vmax. I think they gave it to us as 340. And this is in your square root. The square root 2 remains there because that VRMS means that is the root mean square. So my Vmax was given to me as 340 from my question paper over my square root of 2. So I'm just going to not use a calculator. I'm still not going to take it there. That gave us 240,416. And then I can say, now that I've got my VRMS for my toaster, I can say my average power that's required by my toaster, the root mean squared, and then my current IRMS. So the power for the toaster, let me look for I as a subject of the formula. So I'm going to divide both sides by VRMS, divide this side by VRMS, this and this will cancel. So IRMS is actually equal to PAVE all over VRMS. So the power for the toaster is 800, and my VRMS is 240,416. Just to take you back here, we also ended up with 800 over 240. I'm not going to use a calculator, just so we don't waste time, and then I'm going to get 3.33. And current is measured in amps. We use an ammeter, but it's measured in amperes. Okay, so that is the next question. So let's see what the other question was asking us. So that is for the toaster. My next question says, I must calculate the total RMS current delivered by the generator. So now I want us to look at this question. So the toaster will have its own current, right, which we just calculated. Now I need to find the current that the kettle will require, meaning I'm using the same procedure. I know that my Vmax is 340. It's exactly the same for my kettle, but now my power has changed. So I can use any of the formulas we've just used. If I can find the current for this one and the current for this one, I add the total current. Taking you back when we were doing electricity, if you have your current that is in a parallel circuit and your current is branching off into different sections, right? We are able to calculate the current in this one and the current here and the current here to find the total current of that circuit. So if I know the current that is coming through, there's a current there, and it also goes, and it goes, and then the current comes, and then here we're going to have one form of current, or the total amount of current. So I must find the current already for the toaster, I'm going to find for the kettle, add them together, and then I'm going to find my final answer. So let's see what we're going to do. Let's find for the toaster. So let me just say for the kettle here, for the kettle, so that you'll know what I'm doing. So I'm just going to use one. I'm just going to say PAVE. So you can use either of the ones that we've just used. I'm going to say VRMS. You can do it the long way around. Remember, VRMS is Vmax over the square root of 2. The power now is 2,000, and this is for the kettle. I'm going to say 340 over the square root because they've given me Vmax. I am looking for the current. I'm going to have 2,000 on this side. Taking it back from the previous one, I think we had 240,16416. We had 416, and we had IRMS. If I'm looking for the current of the kettle, I'm going to divide both sides with what is irritating it. I'm going to divide both sides with 240,416, and on this side again, 40,416. This and this will cancel. So I'm left with IRMS for the kettle. Let's calculate how much we're going to get there. I've got 2,000 on the top, all over 240.416. I get a current of 8,32. Remember, you need to round off, and current is measured in amps. So now I'm looking for the I total. Remember, the total. I'm just going to do it the long way around. We had a toaster, the current for the toaster, and the current for the kettle. Now, the current for the toaster, we got the 3.33, if I'm not mistaken. And for the kettle, we've got 8.32. Let's see how much we're going to get there. 3 and 2 give me 5. 3 and 3 give me 6. I'm going to have a comma. And then 8 plus 3 gives me 11. And I total will give me, we measure current in amperes. So the I total is in amperes. So looking again at your formula sheet, there's actually another way we could have used to calculate it. So we could have said the power average, the PAVE, and in this case, I want to tell you how I think we can do it. If we know how much power this generator is then getting, we can then find the current that is required for that power to be distributed. So now let's try it that way. So I can have my power, I can have my VRMS, and I've got my IRMS. Remember, I'm looking for my IRMS. The power total, if my toaster is 800 and my kettle is 2000, it means the total power for that generator means it's 2800. I'm just adding it together. So I'm going to have, let me just do it the long way around. I'm going to have 2000 plus the 800, just in case you don't know I'm getting it. I'm looking for, this is the total power. And then for my VRMS, remember they told me Vmax is 340 over the square root of 2. I am looking for IRMS. So then I'm going to have 2,800. Just move down. I'm going to have 2,800. Taking it back to our equation here, I'm just going to steal it there. It's 240,416. You're going to get used to this number a lot, my darlings. Trust me. I've got IRMS. Now, I'm looking for the total current. I'm going to divide both sides with what is irritating the IRMS, which is 240,416. What you do on the left-hand side, you do on the right-hand side, 416. This and this will give us 1. So my IRMS, let's see what we're going to get there. So we're supposed to get, we are supposed to get 11.65. Let's see if we're going to get that. On top, I'm going to have 2,800. At the bottom, I'm going to have 240.416. Shabuya, there we do. We have 11 point, yes, there we are. So we're also going to have 11.65. And remember, we measure current in amps.